Hello, everyone. I hope the beer was good. And today we are on a data science festival. So I hope it's not surprising that I will talk about data science. But I will talk about data science from a little different perspective, from the perspective of software engineer. Just to warn you, and I think I should warn you that today you will not learn anything new about statistics. You will not learn anything new about R language. I think that this talk shows you some lessons which we have learned during doing our data science, and these things will also help you to avoid some mistakes which we already made. Few words about me. I am data scientist at Ocado, and right now I am working on an internal NLP project with Maciek, Martyna, and Kuba in Kraków office. Feel free to contact me by this email. And just for the sake of this talk, I'd like to make a deal with all of you that for next 40 minutes, you will need to take a perspective of software engineering. So all of you right now are software engineers, okay? So let me start the whole presentation again. First, how many of you are software engineers? Excellent audience. So I will start the presentation again. How many of you are data scientists? Okay. And how many of you already use the TensorFlow or know something about TensorFlow? Oh, excellent. Okay, so let me introduce Mark. Mark is a just ordinary data scientist. He has a PhD in statistics. He did some Kaggle competitions. And he also finished some courses about machine learning on Coursera. What is the problem with Mark? Okay, you already know the problem. We hired him because he seems to be an excellent candidate for our new data scientist positions. So he started building his model, and after a long time, he made a model. And of course, the model was excellent. He announced that this model has more than 99% of accuracy. So everyone in the department was excited. And the last thing we just left to do is to deploy this into production. And Mark is a data scientist, so he just created the ticket for software engineers. Please try deploy this. And as an attachment, he adds a few R scripts and few papers, just to explain the maths behind. And what is the problem? Because right now you are all software engineers. So what is the problem with this code? It's obvious that it just can't go into production. Why? Because the code was extremely dirty. Engineers need to rewrite it almost from scratch. The second thing about this code is that it was written in R, and sometimes the things are very easy to express in R, but it's much harder to implement in real life, in real system, which in this case was written in Java. And especially it's hard to express some transformation if you need to deal with low latency. So the whole solution where engineers rewrite it, he did math and models, was just impossible to maintain. So after the Mark case, our engineers have a new mantra that sometimes it's better to have a model with 90% of accuracy in production rather than 90-90, but only on the paper. after the mark case, we need to sit down and try to define what is the final results of data scientist work, paper or software. And our answer is data science is software, at least from software engineer point of view. And what we mean by that? And when you just start treating your data science and all what you do as just software, magic happens. Yeah. Why? Because the software engineering and building the software is a very mature area of technology, very mature area of business. So you can easily take the best practices from software engineering world and easily apply them to the data science community or data science stuff. And what are the best practices are? You can easily find the successful library on a GitHub, and every one of those libraries will be first version control. It's obvious for every software engineers that code has to be versioned. And many data scientists just forget about it because it will use only once or something like that. So there are a different explanation. Second, tests. If you don't have tests for your transformation or for your code, you just can be sure that it will run and it will work like it should. So test, you have to write a test even in machine learning. The CI environment. How many of you heard about CI or know what this means, the continuous integration? Okay, so continuous integration environment is a place where you as a data scientist or software engineer can check if your project will work on a different machine than your local machine. And you will check this in a continuous way. So for example, after every commit, the job will start and we will check if all tests just passed, okay? CI environment is one of the common practices in every open source project. So definitely we should learn from project on GitHub. The code review. It's a common practice in software engineering world, and from my experience, even statisticians can write a clean code. But first you need to show them how. And some coaching will be needed here, but statistician can write a clean code. What software engineers normally do when a customer reports a bug? Sometimes we just answer that it's not a bug, it's a feature. But normally what we are trying to do is try to reproduce the bug on our local machine or on a dev environment. Why we do it? Because to fix an issue, we need to first understand why it happened. And the best way to understand is just to reproduce. And if we have some problems with reproduction, we always try to gather more data. Maybe we will add some logging. Maybe we will ask customer for additional parameters or something like that. John Ioannidis, who is a professor of medicine at Stanford, claims that most of published research findings are false. And the funny thing here is that he and his colleagues analyzed many papers in different fields of science, and they analyze these papers to check if they can get the same results as authors claimed. And sadly, only in small percent of papers they were able to do that. And according to the professor, the problem sits in reproducibility. By the way, the professor talk is on YouTube, so I really recommend it. It's nice stuff. And during the watching of this video, I've started to wonder if anyone tried to reproduce his research, because we have some inception here. Okay, so we have defined that problem sits in reproducibility. And what are the benefits of reproducibility in your department or in your organization? First, you will have much more confidence about your results. Second, data scientists can easily change the project. And I think it's important because these guys, I mean data scientists, always want to learn something new. So the best way to allow them this learning is to let them change the project. If you still don't believe Ioannidis' claims, you can also just take a random paper, and you will find at least one paragraph, random research paper, and you will find at least one paragraph where author just try to convince you that his method is the best, his method is the state of the art. But yeah, there is, unfortunately, it's really rare that you will find even one line in papers how to really reproduce these papers, yeah, how to reproduce the results. So we know the benefits for organization, and we need to make our research reproducible. So how we see reproducibility? So for us, it's data plus code plus environment plus decision. Let me explain this. To get the same results every time when you run your experiment, you need to use the same data and you need to run the same code. And of course, this code needs to be run in the same environment. And let's go into detail for every of these components. So first, data. There is only one rule here. Just make a copy of everything. And I mean everything, so it's not only the raw data, but also transform data, aggregated data, yeah, and anything which your models produce, anything should be in your storage. And I've put the logo here of Google Storage because we are using Google Storage a lot. Nowadays, cost of storage is just nothing. It's extremely low. So don't think, just push the data into the cloud. And in case of storage of data, it's very common that data will change during the project. So you just use some data set, and after a while, this data will change. And the problem, if you don't have the real copy of everything, is that it will be impossible in the future to come back to the previous stage of the research if you don't have this copy. So rule number one is just copy and just have this data. Second, which I mentioned earlier, for us, data science is software. So it's obvious that we need to have every code, everything which we have created in a Git repository. And I've said everything that, because it's not only the machine learning or modeling stuff should go to the repository, but also the SQL queries, the data transformation, scripts to download data, everything should be in a repository. The third thing is environment, and sometimes it happens that you run the same code with the same data, but you will get a little different results. Why? Because environment has changed. And it could be that some library which you are dependent on has changed, or it could be that someone like administrator just upgrade the systems. So you need to have a way to keep your environment clear. And this problem, I mean the changing libraries, the upgrading of the system, is the reason why the Docker was created. Have you heard about Docker before? How many of you? Oh, excellent. So for all of you who are not familiar with Docker, Docker is a container technology which allows you to specify how your environment should look like. And the Docker will be responsible for the setting up this environment for you and running this in isolation to others, people and others' environment. So definitely after a presentation, it's a technology to check. The last thing which gives us the full reproducibility is the decisions. And it's tricky to explain because the results of data scientists' work is not only the final model. You need to also keep all your decisions which you have made towards this final model. So you need to have, we as a data scientist, we every day made a lot of decisions about parameters, about the architectures, about many different things. And you need to somehow store these decisions to allow the new data scientist or new joiner easily jump into the project and understand the whole process of thinking rather than only the final model. We have decided to use the Jupyter Notebook. I think all of you are familiar with Jupyter Notebook. And why we did it? Mostly because it's easy to rerun the part of the notebook, and also it's easy to store the chart there. So all our decisions are in a Jupyter Notebooks. The environment is separated through the Docker container. All our code is in a Git repository, and all our data are in Google storage. Okay, so the lesson 2 from today is there is no data science without reproducibility. And lesson 3, which will be the last one, is a very quick one, and I would call it, when you are doing data science, just don't forget about automation. Every data scientist wants to work on a research project, wants to build a new model, check a new methods, or check the new algorithms. But many of these data scientists will just waste their time. Why? Because they are so focused on modeling phase that they will do a lot of different, they will do a lot of things manually in a different parts of the project. The example of this really bad behaviors are, first, many data scientists still download the data manually, because they are still believe that they will download this data only once. And you know that it's a stupid belief. Second, this type of bad behavior is a lot of data scientists still train their models on local machines. So they just run the training and watch how the metrics looks like. Yeah, so it's just a wasting of time. And rather than spin up the cluster or instances in Google, they just heat their rooms. Yeah. Okay, so the third example of this stupid or bad behavior is looking for hyperparameters. We need to, because our models use the hyperparameters, so we need to somehow find the best parameters. And many data scientists try to manually find them, rather than just specify the whole ranges for each parameters and let the search algorithms do the work. So just like you see, not all data scientists thinks about automation. And if there is only one thing which we as a data science community should learn from software engineers, I think it's automation and proper using of infrastructure. So just to sum up, we have 3 lessons from this. The first, data science is software. The second, there is no data science without reproducibility. And third one is don't forget about automation and proper using of infrastructure. So in the abstract of this talk, I've put the info there that I will show you these lessons and these advices on real world example. So right now it's the time for that, and I will show you our internal NLP project. But first, we need to discuss a little bit about how our contact center works. thanks to Paul Clark introduction, you already know that we, Ocado, we are just online grocery retailer. And so we don't have a physical shops. Our customer just can't touch the product. They also just cannot ask saleswoman for help. So to be honest, we have only two real points of contact with our customer. First is when our driver comes to your home to deliver your food. And second, when you call us or write us an email through our contact center. And I don't need to say that these points of contacts are crucial for business to keep the customer happy on both of these contacts. So we will today focus on a contact center. And our customer write us emails about almost everything. Some of them just write us to inform that they will be out of home, so the delivery is impossible. Some of them just ask us for adding new product. Some of them just raise an issue about website, and others just want to give us a feedback. Just like you see, not all these emails are equally important in case of priority. So it might happen, because right now we don't know the content of email until one of our agents from the contact center read this email. We don't know the content of email. So it might happen that you will write us an email, and it's crucial email for you, and this mail will wait in a queue for 6 hours or even more, because we working in a FIFO manner. So first in, first out, or in other words, first in, first served. And this model of work is not reasonable, especially in a long term when we want to sell this technology to other retailers. So we need to find a better solution, and the answer for this is machine learning and natural language processing. Please imagine the machine learning models which read the email and return the list of tags. Then contact center application can use these tags to determine the real priority of the email. So just like you see, this email is not a very priority for us, especially during hectic days. We need to build this model somehow. So the whole problem from the data science point of view or machine learning point of view, this problem is well defined, and it's a multi-label classification problem of text or text categorization. And we have read all recent papers in this area of problems, and we find out that almost all good results are achieved by some deep learning techniques. So we have checked the papers, and we found that we need to try at least 3 different architectures for this problem. The first one, the logistic regression with just a bag of words. We will treat this model as a baseline. And others are convolutional neural networks with embedding, and the long short-term memory model with embedding. As an embedding layer, we have used the word2vec algorithm on our corpus. For all of you who are very interested in how these models really works, you need to attend another talk, because today we are software engineers. So we will talk about technologies. And we built these models in a Python and TensorFlow. Why Python? Python is language #1 in a data science community recently. It has nice syntax, it has huge expressiveness, and thanks to libraries like Pandas, NumPy, and recently released TensorFlow, this language has big opportunities in the front. So we built the model with Python, but also in TensorFlow. And for all of you who are not familiar with TensorFlow, TensorFlow is open source library for numerical computation. You just specify the graph there, and TensorFlow will run this graph. You just specify this graph in a high-level API in Python, but all operation and computing stuff will be done in C++, so it will be extremely fast. And in case of deep learning, it's a crucial thing because deep learning needs a lot of computation. You need to backpropagate gradient there, so it's a lot of computation there. For all of you who are familiar with TensorFlow, because I've already seen you that I've prepared some tips for you, which we already learned. That first, never try the object-oriented programming in TensorFlow. Because you need to specify graph there, it's really hard to debug your graph later when it's built from the classes and inheritance rather than a small functions. So it's much better to build your graph through the chain of functions. The second thing, since the version 0.9 TensorFlow, it has native support for Google Storage. So you can read your data and write your data directly to Google Storage. And third, Flags module. How many of you heard about the Flags module in TensorFlow? Okay, so maybe I shouldn't mention this because it's so small that maybe it's stupid to just mention this. But Flags module is responsible for passing the parameters from command line to your model. So you just specify the name of the parameter of your model, and you also specify the type of the parameter, and Flags will just pass the value for the parameters to model. And you will see on the next slide, but it's crucial to have the one place where all your parameters are gathered. Yeah, that's all for all these TensorFlow geeks. And let's see the whole solution, because I've said that we're treating data science as a software, so you have the architecture of whole our solution. Contact center just if they get the email from customer, they just ask us in web service, ask us what are the tags for this email, and we just predict the list of tags, appropriate tags. On this slide, you can also see how we train our models. So the web service is only the serving layer. But we train our models in a Google Compute Engine and through technology Kubernetes. So we use the power of cloud to really train these models. And of course, we read the data from Google Storage. And also, we export the model to Google Storage. So everything is kept in Google Storage. How we are assuring the reproducibility, because I've said that the second lesson from today is there is no data science without reproducibility. So how we assuring the reproducibility? First, you can see almost all components which I've mentioned. There is a commit here, so you all exactly know how the code should look like. There's environment there, so you have a link to the Docker image. You have a data there, so you can know which data should be right and where the results should be saved and which data should be read. The model parameters just decide which models we should run, and the parameters are the flags from the flags module. So it's this one place where we keep all parameters. And yeah, for every model, if you just keep this very simple JSON, the reproducibility is not a magic. Because to reproduce your results, you just can write a script which will set up the environment, download the proper commit, and then start the model with the parameters. So you will get exactly the same answer every time when you run it. Because of this small, very simple JSON, thanks to them, we can also automate our things. Because in this simple JSON, you have seen the whole definition of the model. So you can easily generate this kind of JSON and run them in the cloud. Have you heard about the technology Kubernetes? How many of you? Okay. So Kubernetes is also Google technology, which allows you to set up the cluster of instances in Google and lets you define which Docker image should be run on these instances, and Kubernetes will be responsible for, if some of these instances are dead, they will just restart it. So it's some kind of the cluster manager. And we use this technology to really train our models. So it's very simple to use if you have a Docker image. Okay, so that brings me to the end of the presentation. So just to sum up, there are the key takeaways for you. Data science is just a software. No science without reproducibility, and of course, don't forget about automation. Thanks for listening, and enjoy your rest of the evening.
Did we have any questions?
There is.
There's always questions. Come on, sir. I think we'll have to shout. I'll repeat it. Come on.
Speaking of reproducibility, have you tried Jupyter dashboards?
For what?
For reproducibility, because it's one click to web app.
Yeah, but it's all only, you will have just only the IPython things there, yeah? Not the, we could use it, yeah? But it's only in a small percent of our reproducibility, because you still need to have the environment when our model will run. You need still the code in the repository. So just for decisions, I think it's a good choice. But from the whole image of the reproducibility, the IPython dashboard is a nice last one. Yeah. So definitely worth to try. We didn't do it because we used only the very simple IPython notebook to just keep decisions there. Yeah. Small charts. Very simple scripts, because I think it's worth to mention that it's not easy to store the IPython notebook in a repository, because you have the charts there, etc. So we try to move as much code as we can to repository, and in a IPython notebook we'll only just call the functions from the repository. So there is no real science there, let's say. It's just only the decisions.
Okay, the guy in the blue shirt.
So I have two questions. One question is about the data versioning. So I agree that's a good idea, but I'm wondering how you do it in practice, in the sense of how do you keep the versioning similar to code versioning, or that if you have a lot of updates to the data which we're using, like in the case of emails, you might want to retrain your model with, every 100 new emails or so. Do you store just deltas or the whole data set again?
Okay, so
what kind of technology do you use for that? And the second question is just briefly about what you use in terms of hardware infrastructure for the the neural networks use GPUs for that, or do you just is it not necessary?
Okay. So for the first question about storing data, it's a good question because if your data set is changing in real time, it's really hard to track all these changes. So we have decided to for every data which we have, we generate very simple and which is similar JSON to model setup. We call this data setup, and we keep the all information and metadata about this data set, because we always make a copy, yeah. So you will have just another bucket, just another bucket, just another bucket because storage is cheap, and the only thing which needs to assure and be sure that you still can manage somehow this data. So you need to store metadata about this data set. So you need to know from which data set that part of data was created, or from what parameters was used to generate this data. Okay, so this is the first question, and the second question about the using GPU in deep learning stuff. So in case of using GPU rather than CPU or something like that, we have a opinion here, which is I think it's quite popular one, that you don't really need the GPU because the GPU is a little, maybe 4 times faster than CPU, but in case of cost, it's not as good as a CPU. So it's much easier to run a very big number of models in parallel to find the best hyperparameters or something like that, because you also can make a hyperparameter tuning through the parallelization, yeah. And all of these machines can be just ordinary machines, yeah. Answer the questions?
Yeah.
Cool.
Okay. There's one guy in the back with the black shirt.
How quickly can you deploy a new model if you come up with something better?
Oh, it's a good question. So in case of the TensorFlow and the exporting the model, in a TensorFlow you just define the graph, and not only define the this graph will compute some kind of variables. So it will be just huge matrices, which then TensorFlow during prediction will just multiply them. Deploying a new model is as simple as exporting the new matrices and new graph definition. So in this case, it's very simple to export it, and it just do it in a second, because the training phase can take a long, because you need to compute these matrices, yeah. But when you finally have there, you just can easily export them. Okay.
Okay, we'll maybe take 2 more questions,
Okay.
and then we'll break it up from there. So
Sure. The
guy
beer is waiting.
middle at the back, yes.
Two quick questions. So one is about the reproducibility. Are you trying to get reproducibility down to numbers? So like you specify a Docker container, specify the seed and everything, so that it would return the same number to like the floating point. Is that the idea? And the second question, what sort of automated testing are you using for stochastic algorithms? Because you're making like sort of predictions, but you have a test suite. So can you elaborate more on that?
Okay, so about first question, it's a good notice that to really reproduce the results, if we have some kind of random process inside the model, we need to somehow be sure that random will still be the same, yeah. After randomization, so we keep the seed as a parameter, and all our random are not random, yeah. So we only really random the seed, yeah, and that's all. And the second question, because I can you just remind?
So the automated, so you have a sort of stochastic prediction process, right? So to what extent do you test the new deployments of what's sort of your test suite on the new deployments of the old? Because
Yeah. If I understand your question correctly, it's hard to really automatically test it. So we mostly focus on preparing the tests, automatically test for transform data or for anything which we do with data. But the machine learning phase, it's much harder to really test. So there are some solutions for this when you just specify some kind of constraint where the result should be. Yeah. So there are some libraries for this, but right now we are using only the PyTest library to make just ordinary tests. Is it answered? Okay.
Right, we've got one more. Is there one more? The very front. Come on, sir.
Yeah. How do you deal with knowing that you've made a better model to classify your emails? So particularly with regards to how you choose your test set. So say you create one model, you test it against the test set, it's the best model you've got. 6 months later, maybe you've released a different product, you're getting different types of emails in. How do you know your new model to classify these emails as better? Do you use the same test set? Do you update your test set? And how do you make that decision?
So really good question, and it's not a question only to me because it's a common problem in machine learning world. What about the changed data set? My opinion is that if you can backtrack, so you can test your previous model, and thanks to reproducibility, you will be. You can just, after a while, when you will gather the new data set, you just compare at the one point of the time. So let's take recent data and let's compare the model right now. So thanks to reproducibility, you can check also all previous models. And every day you can just decide which version should go to production. And this is the answer, but it's not easy to implement it in real life. So many times, because machine learning is used by real people. So agents start reading these tags. We just automatically sort the queue. So it's not easy to really changing this version very frequently. Yeah, because some people are they are start adjust to the behavior of the machine learning. So you need to build trust in this machine learning, and yeah, that's all what I can say here.
Okay, thank you very much, Marcin. That was awesome. Thank you.